All right, guys, so in this video, we're going to go over the last two questions on the most recent AP Chemistry exam that was taken on May 6th, 2025. And again, if my students are watching this, or West Springfield High School students are watching this, hey, this is good review because you're about to take the exam on May 21st. If you already took the test, then, hopefully you are getting the correct answers. All right. So, number 6, pretty straightforward, galvanic cell, voltaic cell, electrochemistry question. Nothing too crazy about this one. So, first of all, it says write the half reaction for the oxidation that occurs at the anode. So first we have to figure out which one's going to be the anode, and that's going to be based on these potentials. So we have a zinc cell and we have an aluminum cell all set up at standard conditions, and we just have to know which one we have to reverse, right? We are only given reduction potentials, so we're going to have to flip one to make it an oxidation potential, and you always want cell potential to be positive. So you're always going to flip the more negative potential, because then that'll make it positive, and then when you add positive this to negative that, you end up with an overall positive voltage, right? So first off, we need to know some definitions. Oxidation occurs at the anode. So the aluminum one is the one we're going to flip. Right now it's a reduction potential, but we're going to reverse the reaction and make it an oxidation potential. And that's the reaction. Oxidation is what occurs at the anode. So it's the aluminum that's going to be oxidized. So this is the anode, and the reverse of this reaction is what's happening at the anode. Okay, so it would just be aluminum yields aluminum 3 plus 3 electrons. Okay. Another thing to remember is when you reverse a reaction, you flip the sign of cell potential, but if you double or triple or whatever a reaction, you don't change the cell potential. You would change it if it was delta H you were working with, but not cell potential. Okay, so then it's just asking you to write a net ionic equation for the overall reaction that occurs. So remember, the electrons completely have to cancel. So we have to reverse this reaction, right? Just like we did here, right? So that's our oxidation half reaction. And then this is our reduction half reaction. But before we add them together, the moles of electrons have to cancel out. So we're gonna have to multiply these coefficients by 3, and we're going to have to multiply these coefficients by 2, so we end up with 6 moles of electrons canceling out completely. So you're going to, again, triple this equation, double that equation, then add them up. The electrons will cancel, and this is the overall reaction that's happening. So 2 aluminums plus 3 zinc 2 pluses yield 2 aluminum 3 pluses plus 3 zinc atoms. Okay? C, initially each electrode has a mass of 50. So this zinc electrode is 50 grams, this aluminum electrode is 50 grams. The cell is allowed to run for a period of time and is then stopped. Which electrode's mass changed the most? Justify your answer with a calculation, okay? So first off, let's just understand, as the reaction proceeds, we're gaining zinc, and we're losing solid aluminum. So we're gaining solid zinc, we're losing solid aluminum. And if we go back, the solid zinc is coming from the zinc 2 plus. So the zinc 2 plus from this solution is going to plate on to this zinc metal, and you're going to get more zinc metal onto this electrode, okay? At the same time, the aluminum atoms in this piece of metal are going to release their electrons and then dissolve into solution as aluminum 3 plus ions. So this electrode is going to lose mass. So the aluminum is going to lose mass because Al is becoming Al3 plus in the solution. And this electrode is going to gain mass because the zinc 2 plus, as it's being reduced, is going to plate onto this piece of metal. So the zinc's going to gain mass and the aluminum is going to lose mass. And we want to know which one's going to lose more mass, or which one's going to not. So is the aluminum going to lose more mass than the zinc gains, or is the zinc going to gain more mass than the aluminum loses, right? And so first, it's stoichiometry. Second, it has to do with molar masses, right? So understand, for 1 mole of the reaction to occur, we're going to lose 2 moles of aluminum, but we're going to gain 3 moles of zinc. So 3 moles of zinc would be plated on to the zinc electrode, but the aluminum electrode would lose 2 moles. And that's for every 1 mole of the reaction. Now, it's impossible for 1 mole of the reaction to occur because we're only starting with 50 grams, but the idea holds true. So what I'm saying is 1 mole of the reaction consumes 2 moles of aluminum, but produces 3 moles of zinc. 3 moles of zinc times the molar mass of zinc is 196 grams. 2 moles of aluminum times the molar mass of aluminum is only 54 grams. So if 1 mole of the reaction were to occur, the aluminum would lose this much mass, the zinc would gain this much mass. Okay? Now, 1 mole of the reaction can occur, but no matter how much the reaction occurs, the zinc is going to gain more mass than the aluminum lost. Okay? So the aluminum electrode would lose less mass compared to the mass gained by the zinc electrode. And, that's kind of the calculation. Now, you probably want to show the calculation, like 3 moles of zinc times the molar mass of zinc, which is what, 65.41 or something, and then 2 moles times 26.98. But that's what's going on, okay? All right. And then part D, so we're going to make, so the standard cell that we were just looking at has a voltage of 0.9. Okay, we want to make a galvanic cell with a greater voltage, and this is what the scientist has available to them. And we want to know, well, instead of aluminum paired up with zinc, what if we paired something else up with zinc? Could we get a higher voltage? Okay. So notice it says nothing that, it says he still needs to use zinc as a half cell for the reaction, but it doesn't say the zinc has to be the cathode or the anode, right? Right now, the zinc's the cathode, okay, of the aluminum zinc battery. Aluminum's the anode, zinc's the cathode, okay? But what you could do is see that the gold is much more favorable of being reduced. You could pair it up with the gold, and now the zinc would be flipped. And the zinc would be the anode because the zinc would be oxidized and the gold would be reduced. So that's your best option here, because you would flip the zinc and that would become a positive 0.76, and then you would just add it to 1.5, and that would be our answer to part D, okay? So the answer to part D is the maximum voltage we could get from any possible combination of zinc reacting with one of these half reactions would be zinc paired up with gold, because the zinc would be flipped and that would be positive, and it would be positive this plus positive that, and 0.76 plus 1.5 comes out to be 2.26 volts. So the answer to D is 2.26 volts, okay? But in that case, zinc would end up being the anode, but it doesn't matter. It's just we're using zinc as one of our cells. It doesn't matter if it's the cathode or the anode. We just want the maximum voltage based on whatever else we have to deal with, okay? All right, so now let's go to number 7, okay? So number 7, they give us the Lewis structure of a base, and we want to circle which of these atoms accept the H plus from the water, okay? And so it's always going to be this oxygen that has the 3 lone pairs on it, right? Next to the oxygen carbon double bond, right? Because remember, if you add an H plus to this, that ends up being your carboxylic acid functional group, and that acid, once you add an H plus to here, would be the conjugate acid of this base, okay? And so, going back and reviewing that little bit of organic chemistry that we do back in Unit 1, knowing what a carboxyl group is would help you identify, oh, the H plus would go here. It's not going to go here, and it's not going to go here. It's going to go there, okay? So that one. Remember, and now that you've added the H to it, right, so that's going to be the one that takes the H plus away from water, and that's a carboxylic acid functional group. So that would be the conjugate acid of this base, okay? So then they show us the equation of it acting like a base in water, and they give us the equilibrium constant expression for the reaction, which is the Kb expression for this base, okay? And it's asking us, it's giving us the concentration of this that we're starting with, and it gives us the concentration of hydroxide, and it's asking us to calculate the Kb, okay? So this is where I would tell my students to use their Kb shortcut, and you would say Kb equals x squared over the concentration of the base. Now, we're gonna be able to 5% rule it, but if you wanted to, you don't have to 5% rule. You could say Kb equals x squared over the concentration of the base minus x, where x represents the hydroxide concentration. Remember, in this Kb shortcut, which we know, right? So they gave us the concentration of the hydroxide, they gave us the concentration of the base, right? So if I don't want to do the 5% rule, I would do 1.3 times 10 to the negative 5 squared, because remember, for every 1 mole of hydroxide, we get 1 mole of this. So whatever the concentration is of a hydroxide, that's the concentration of this, the conjugate acid. And then the initial concentration minus the hydroxide concentration would be what this concentration is at equilibrium. All right, so that's where we're doing 1.3 times 10 to the negative 5 squared divided by 2.5 minus 1.3 times 10 to the negative 5. Now, this is so much smaller compared to 2.5 that we can just call it 2.5, and that's where the 5% rule comes in. And notice, whether I don't use the 5% rule or I use the 5% rule, I still get the same answer when I plug in. So this would be the value of Kb based on the information given, okay? If you're gonna use the 5% rule, I would write this, I would like show what I'm thinking, and then I would, say, maybe circle this or underline it and say 5% rule, and then you end up with the same answer, okay? Using your answer from part BI, calculate the Ka. So this is just remembering that Kw equals Ka times Kb when you have conjugate base pairs. So we always know Kw, 1 times 10 to the negative 14, and then we'll divide it by our answer here, and that'll give us Ka. So we'll do 1 times 10 to the negative 14 divided by 6.8 times 10 to the negative 11, and that's where we get the Ka for the acid, 1.5 times 10 to the negative 4, okay? All right, so here we got another unit 7, our unit 7, kinetics question. So they give us a mechanism, okay? And remember, this is all about knowing what an intermediate is versus what a catalyst is in a reaction mechanism. So remember this thing, C2H5O3+, that thing would be classified as an intermediate because it gets produced and then it gets consumed. That's an intermediate. Mechanisms have intermediates. Not all mechanisms have catalysts. A catalyst is something that doesn't end up in the overall reaction, but it's in the mechanism, but instead of being produced and then consumed later on, it's used initially, it's consumed, and then later on it's produced. So remember, an intermediate cancels out on this diagonal, a catalyst cancels out on this diagonal. You don't always have catalysts, but H3O plus would be a catalyst here because notice it's not in the overall reaction, so it canceled out, but it started out as a reactant and ended up as a product, and that's a sign that it's a catalyst, okay? So C, here we're agreeing with the student again. The student claims that H3O plus is a catalyst for this reaction. Do you agree or disagree? We would say, yes, I agree, because H3O plus is a catalyst in that mechanism. Now, to say it in words, the way I would say it is H3O plus is used and then produced through the mechanism, but is not a reactant in the overall reaction, okay? So if something is in the mechanism, but it cancels out when you add everything up and it's not a part of the overall reaction, it's either an intermediate or a catalyst. An intermediate gets produced and then consumed later on. A catalyst gets used first as a reactant and then gets produced later on as a product. And again, in a multi-step mechanism, you'll have intermediates, but you don't always have catalysts, okay? But in this case, we did have a catalyst, and it was H3O plus, all right? All right, so that's the AP exam, guys. Well, the free response. So who knows how the multiple choice was? I don't know. The free response seemed, I don't think it was as easy as last year's, but it was pretty straightforward. I think it was more straightforward than last year's, but I think last year might have had a few more easy questions. This one, if you do a good job reviewing, it's pretty straightforward. So, if the free response is like this, maybe the multiple choice is more difficult. Okay, I don't know. So anyway, have a great day and good luck with whoever took this exam. Good luck on your scores in July, and if you're gearing up for that May 21st exam, hopefully this will be good review for you. All right, have a great day.